So we are now going to study the wave chapter, and if you recall, in the wave chapter we began with the types of waves. Now, to understand the types of waves, we have to understand certain more concept known as your vibration, known as your oscillation, and known as your wave propagation. Okay, so let us understand first what exactly is a vibration or an oscillation. So basically these are nothing but to and fro motion. Okay, so for example, let us say you have a simple pendulum, and the simple pendulum moves all the way, from here to here, and then back from here to here, and then again back here. So the simple pendulum moves this way, right? Now this is called a to and fro motion. You can see the same thing on a spring also. So if I have a spring here, and if I have the spring, let us say a normal spring at this point, and if I pull the spring downward, then the spring would basically become something like this, right? And if I let him go, it will climb up and it will get compressed somewhere here. So you will have something here, and then you have the compression here, and then you have that expansion. So this movement, once it goes, let's say, up, then comes down, and then goes up. So it goes like this. So it goes up and down. That is called your vibration. So that is your vibration. Oscillation basically means your one cycle of vibration. So one cycle of vibration means, let us say you began at a point here which is A, you went to B, then to C, and then back to A, and then B. So you are covering all the way here to here, and then back here. That is called your one cycle. Okay, this is called your one cycle, one full cycle. Now that is your oscillation. Same thing in the spring. Spring also goes up, comes down, and then goes up. So that is called one cycle of vibration, which is your oscillation, the name given. So we are going to use this name oscillation all the time. Okay, what is wave propagation now? So let us say, for example, we have water. So we have water on this surface. Example. Okay, I'm going to discuss example, and in the example I have water here, and I take a stone and drop it at this point. Okay, I'm dropping a stone. So this is basically a stone. When I drop the stone in the water, I can see the water moving around in certain ripples. So I can see these circle structures like this, and I can see that the wave is traveling something like this. See, it travels like this, and it travels in all direction like that. Okay, in every direction it goes, the water, and these are known as your ripples. So when you drop the stone, the ripples are created and the wave travels. Now that direction of the wave is known as your wave propagation. So the direction in which wave travels is known as wave propagation. So propagation is nothing but basically a movement, okay, movement of wave. Now let us start the types of wave. Basically there are two types of waves here. So if I have to come to the types of wave, the first type of wave, let us say, is longitudinal wave. Longitudinal wave. So what exactly is a longitudinal wave now? If I produce a sound, right? This is my mouth. I produce a sound. The sound is going to travel in this direction, right? So sound travels in this direction. But sound won't travel just like that. Sound requires some medium here, and in the medium sound will create a sort of compression, a compression. So sound energy travels in compressions. So at first there will be compression here, and suddenly when this compression goes front, so I will get something like this, which is more spreaded, and then I will get the compression here. See, I will get the compression here. So the compression has come here now, okay? This gap where you see less dense or less movement of the air, or the energy is less here, is called your rarefaction. So sound travels in compressions and rarefaction, okay? Now after some time we will again see the sound getting little more front. So you can see the sound, moving little more front. So maybe the sound will now travel somewhere here. So it is still traveling as a compression. So what happens is, we always have compression, we have rarefaction, and we have compression. So basically a longitudinal wave will be shown as a longitudinal wave has both direction of oscillation or vibration parallel to energy propagation. Energy propagation or wave propagation. Okay, so if you see here, your two directions that we observe is, this is the direction wave travels, that is the propagation, and this is the direction of the vibration. So your vibration happens like this way, and your wave travels this way. So both are parallel. See, both are parallel. So this parallel is the key word here. Now let us discuss the transversal wave and see what is the difference between transversal wave and this wave now. So in transversal wave, for example, so again, if I drop stone in water, now I know ripples are created. Ripples are created. So if I drop the stone here, the water molecules here will vibrate like this, up and down, but then the wave will go this way. See, this is the direction of the wave. So this is the wave propagation, right? And this is the direction of the vibration. This is the direction of vibration. So if you look at both, you will see that both are perpendicular, 90 degree. So in this case, in transversal wave, the wave propagation is perpendicular to vibration. So for example, another example we can give here is that of a guitar, or in a string. So in a string also we have similar situation, right? So let us say in a string, if I tie a string like this with a wall, okay, this is the wall and this is my string, and if I oscillate the string up and down like this, okay, so this is how I am vibrating it, up and down, then there will be a wave motion visible on that string which will go like this. See, so again the wave is moving this way, vibration is this way, they are perpendicular. So this is also transversal. Now let us come to another example which is very important for us, and that is about light. The question is light transversal in nature? Okay, what do we know about light now? We know about light that light has both electric and magnetic field. Okay, these fields vibrate perpendicular to each other. Okay, so if I have a wave, for example, let us say if I have to show the electromagnetic wave, how will I show it now? So I am going to show the electromagnetic wave this way. Okay, this is my electric field, and this is my magnetic field. See, this is my magnetic field. So if I see here, the oscillation or the vibration is perpendicular, right? So because wave propagation is perpendicular to oscillation, electromagnetic wave, sorry, let us not use electromagnetic, let us say light wave is transversal in nature. Okay, now because it has electric and magnetic fields, because light has both electric and magnetic field, field, hence it is also known as electromagnetic wave. Okay, this is very important. So we call it as electromagnetic wave. Now coming back to the wave itself again. We have seen now there are two types of wave. Longitudinal, we saw here up that we have longitudinal, and example of longitudinal was sound. And then we had transversal wave, which is, so many examples are there. We have in the water we see, on strings we see, and the light itself. The light itself is the electromagnetic wave, which is a transversal wave. Okay. Now, there are certain components of wave we should understand. So, graphically, we represent the wave in this form. So, we represent it like this. Okay. This one movement from position A, you went to B and then to C. So you went like this, right? So this is called your one cycle. The cycle already I explained up, if you remember. What was one cycle here? So if I go up, one cycle is if the pendulum goes and comes back to same point, then it is called one cycle. So it goes and comes back. So for this much, one cycle, we represent the wave as like this. So it has an upper half cycle and a lower, okay, half cycle. Now in this half cycle, there are two things that can happen. So one is if this graph shows between the time, okay, and the displacement, and this side is a displacement always. What is the displacement here? You remember, if you throw a stone in the water, it will go up and down. So this is the displacement that it is trying to show here. Okay. So the ripples go up and the ripples go down. Now, if it is time here, so in how much time one oscillation has been made, or one cycle, this is also called one oscillation. Okay. So the time taken for one oscillation from here to here is also called your time period. It is called your time period. And what is time period? It is the time taken for one oscillation. Now let us say some examples here. Okay. So if we write some examples here, a simple pendulum oscillates 10 times in 30 seconds. Okay, what is its time period then? What is its time period? So time period, we know it is the time for one oscillation. So 10 times is 30 seconds. Then one oscillation will be equal to 30 by 10, which means 3 seconds. And this is for each oscillation. And because it is for each oscillation, it is called your time period. Yeah, that makes sense. So let's say another example we can do here so that you can understand whether it is clear or not concept. So the next example, let us take like this. Time period of a spring oscillating is 2.5 second. What does 2.5 second represent, right? How much time will it take for 50 oscillations? Okay, how do we do now this question? So if you look at the question, your time period itself is 2.5 second. What does time period mean? It means it takes 2.5 seconds to oscillate once. Okay, or vibrate once. So if it takes for one oscillation 2.5 seconds, 50 will be how much? Therefore, for 50 oscillation, it has to be 50 times 2.5, which is 5 5 25 to 12 0 decimal. So it will take this much seconds, 125 seconds. This is very important for us. Okay, this is you have to understand the concept here. That's very important. So now we know exactly what we are trying to understand here. So if I go to the mind map once, then now if you see the mind map, you know the types of wave now. Okay, so you have done this types of wave here. Okay, so we have done this part. We have seen vibration and oscillation. We have also seen this. Okay, and we have seen this also. So you know, in the equilibrium, see, the center point is known as your equilibrium. Okay, and then when the spring goes up or down, it is either getting compressed or it is undergoing an extension here. Now vibration in string, already I told you. Oscillation simple pendulum, I have told you. Now wave propagation also I have told you. Now if you see here, it is compression, rarefaction, compression, rarefaction. This is how your sound energy actually travels. This also I have told you. Light, I have told you, electromagnetic wave. So it's a electric field and magnetic field. All vibrate perpendicular to each other. That also I have told you. This ripple in the water also I have told you, that when you drop a stone, there will be ripple, a wave created. Okay, I have told you what is a transversal wave. I told you what is a time period. So time period also I have told you. Now we will just understand what is a wavelength, and then we will see if there are any other electromagnetic waves. So let us go back to this now and understand another concept. So one concept we have seen just now up, which was your time period. So I will just write the topic here so that you know that you are trying to study here. Time period. Okay, exactly. See, now let us see another factor here, which is called wavelength. Okay, wavelength. So what is wavelength now? Let's see. Again, in the water, for one oscillation, you know, when you drop water, a stone on the water, the wave travels like this. So the distance the wave covers in one oscillation. Okay, so this distance covered by wave in one oscillation, is known as wave length. Okay, length of that wave. So important is distance covered by wave in one oscillation. So if this is the one oscillation and if this is the distance I am measuring for the wave, remember there is a difference between this and what is up. At top here it is not distance, okay, it is time here. See, it is very careful. So it is the time taken for one oscillation, and that is the distance covered by wave in one oscillation, what you're seeing down here. Okay, this is the distance covered in one oscillation, and this one is still that direction of your vertical, this particle vibrating here, and this is the wave which is going in one oscillation. So this one is shown with the symbol of this lambda. This is your term called lambda in the Greek letter, and this is your symbol for wavelength, symbol for wavelength. Okay, so for example, let us do one question here, then we will understand easily. So example question. So I have been given two graphs now like this, and let us say they have given me something like this and like this. Okay, and they are giving me another graph, here. Okay, that also is like this, everything same almost the way it looks. And in this data they are giving me here 0.2, 0.4, like that, 0.6, 0.8. So, and they are saying this is time. Same thing here also, they are giving me like 0.1, 0.2, 0.3, 0.4. So here, what is my time period here then from this? So time period is basically the time taken for one oscillation, which means from here till here, and that is nothing but 0.8 second, right? And if I look here, this one they are saying it is the distance. So it's the distance of what? It's the distance of the wave. So what is my wavelength then here? If I see, then my wavelength is equal to one cycle from here to here, which is 0.4. Let's say distance is given in meter, then 0.4 meter. Now if I have to find the speed of a wave, how do I find the speed of a wave? See, the best part is speed of wave is nothing but same distance by time, and what that distance covered is lambda here, and time is time period, because this is the wavelength, which is the distance covered by wave, and time taken by wave. So this is distance covered by wave in one oscillation, and this is time taken for one oscillation. So it will be like 0.4 by 0.8, which is 4 by 8, for example, which is 4, 2 to the 4, 2 4s are, so 1 by 2, so it is 0.5 meter per second. That's the speed of the wave. Okay, so this is how we actually solve questions, simple questions on speed of wave. Now this is about wave, so we are done with the wave. So if you go from again beginning, you can see the types of wave we have seen. So you know now oscillation means one oscillation is full this cycle. You know the longitudinal wave now, where you have your wave propagation and the wave vibration. So your wave is vibrating like this, see, sound in the air, and your wave is moving this way. Both are parallel, that is why it is called longitudinal. And now you also know that transversal is nothing but the wave is going this way, but the particle is vibrating like this, so they are perpendicular to each other. And for example, in a string, if I take a rope and if I move the rope up and down, then I will see the wave like this. So wave is going this way, but rope is moving this way, so the angle is 90 degree here like this. Okay, such waves are known as your transversal waves. And then we saw here down how light can behave like a transversal, because it has electric and magnetic field, and they are all perpendicular, see, to each other. Because they are all perpendicular here, that is why it is a transversal wave. And this is the wave propagation. The wave of the light is moving this way, electric field is going this way, and magnetic field is going this way. Okay, you have to imagine it's a three-dimensional model. It's a 3D model. Okay, a three-dimensional model. And then we saw some simple question. We understood what is time period here, time taken for one oscillation. We also understood what is a wavelength. Sorry, here spelling mistake. Wavelength is the distance covered by wave in one oscillation. Okay, and now we will end with just topic of application of EM waves. See, so we all have done, already you have done a criteria D in this. You have written a essay on this application, and if you recall there, many of you have written that it is used in the medical field. And how do we use in the medical field? We use like X-rays, and we use like gamma rays. Many of you have said gamma rays are high energy, but can cause cancer. In your essay only I have seen this, which is a very good thing. I have also learned from you. X-rays are, you have said that okay, these are used to study cracks in bone. Some of you wrote that safer than gamma, but in long run, if too many time we are exposed to X-rays, then we may develop cancer, right? Many of you have said this. And one of the other use, I think some of you have written here, I remember seeing that microwave ovens. Some of you, I remember you have written here infrared. Microwave ovens are used for cooking. Infrared, some of you said used in remote systems, remote sensing systems, or remote devices, remote control devices. And some of you said it is also used in medical field. They use the heating property of infrared, heating property of infrared is used to heal. And I think overall, if you see, you have demonstrated a good understanding of the EM waves now. So you can read your essay also, because in your essay you have lot of points, and they are very important points what you have written. You also know the advantage and disadvantage of EM waves. Okay, so you have done that also. So we have seen from essay, we have seen advantage and disadvantages of EM waves. You have seen that. Okay, and you have seen some other solutions that you have stated in your essay. I have seen somebody talking of magnetic resonance imaging, which are safer than radiation treatments. Radiation, which means electromagnetic wave treatments, right? So Science is developing, technology is developing, and we all now know that waves play very important role. Very important role in our life, right? And we have seen just now that one of the role of that waves is your EM wave, which is in medical, which is in cooking, which is in radio waves used in communication. We use the radio waves, right? And waves are also like, sound in the musical instruments. We use musical instruments, and we also have waves. We have seen wave in tsunami, the natural disaster. We sometimes see in the earthquakes also. So waves are very important for us to understand, because we have so much of application in real life that we actually we need the knowledge of these wave phenomena. There are so many other wave phenomena that we have not discussed here in detail. Just going to little bit of other things slightly is the reflection and the refraction concept of wave. That part we can just briefly discuss before we close. So for light, we have two things here. One is known as your reflection from polished surfaces. So for example, like mirror. So light bounces back from polished surface. You also did a demo lab. We did the demo lab using the plane mirror. We use the plane mirror, and we have seen in the mirror experiment also there that when you had the plane mirror kept on the paper, and when you brought the light actually reflected like this, right? So this was your incident ray, this was your reflected ray, and this angle we called it as angle of incidence, and this one we called it as angle of refraction. This one we called it as angle of reflection. So IR, and in this case your angle of incidence is always equal to angle of reflection. That's what we have verified in lab. Then later we saw, this was the reflection we saw. Then we also saw the light traveling from one medium to another medium. So light bends when it travels from one medium to another. So there is a change of medium. Change of medium leads to change in speed. Change in speed. In denser medium, light travels slowly. So the speed decreases. As the medium becomes denser, the light travels slowly, right? So if you remember when you did the experiment with a glass slab, so you took a glass slab and then in the glass slab you brought the light from one end, if you remember, okay, like this you brought the light, and then you drew the normal here. This was your normal, the perpendicular, okay, normal which is perpendicular, and then you observed that the path of this light, instead of going straight, it took a bend. Actually it made a bend here like this, correct, and then it took again like this bend, and if you remember, you pulled the line back, this line you pulled it back, and you were surprised to see that these two were actually parallel. You observed that, if you remember in your lab when you did, they were parallel, okay, and that is how the light was moving from here to here to here. So light, if this was air and this was glass, so light bends closer to normal. Now the question is, note as speed decreases in denser medium, the light takes shorter path. It takes a shorter path. So it will go for a shorter path because it has to cover faster. It has become slow, right? So in 1 second it can cover very less distance. So it takes a shorter path. Why? Because the speed has decreased. And then again it goes back to normal path, like here. So the speed, this is again light has gone to the normal path. This is the normal path, okay, but because of this bending it has shifted from here to here. So there has been a shift here, okay, and that is why you see the parallel relationship between the incident and this. So this was your incident, let's say A, let's say B, and let's say C. So your A is called your incident ray, and your B is your refracted ray, and C is your emergent ray. So which comes out, emergent ray. Sorry, I will just erase it because it is not clear. So this is your emergent ray, okay, and as usual I said this one is your angle of incidence. Sorry, I have to draw again. This is your angle of incidence and this is your angle of refraction, okay. So I is your angle of incidence, R is your angle of refraction, okay, angle of refraction. Now application of this we have, like for example, say question, we have seen a demonstration example, demo seen in class. One is bending of object in water. So we have seen this in class. If you remember, we had a beaker. We had the beaker filled with the water. It was all filled with water, okay, like this. And then we had the object. I will draw little bigger object because yeah. So we had the object coming like this, okay. It should have gone this way till here, but it doesn't happen that way. Why? We will see that also now. So I'm going to draw some lines there. Take another color. So from the tip here, this is normal, from the tip here I have another normal here, see, and the ray of light which goes out bends this way, and our eye, which is here, this is our eye, will see the object somewhere here. Okay, so this tip A will appear here as A dash, here, and this tip will bend and come till here. So because it bends, the tip of pencil appears bent. It should be at A, but it is visible at A dash. See, A dash here, it is visible here. Okay, visible here, A dash. So it's no longer at A, it is no longer at A, right? Now this shift of tip of pencil is due to refraction of light, Okay, so think, you can do research and you can think of other examples of refraction of light. So with this, I think we have now ended this unit, and I am sure now that you can understand things better from these notes, and the video has been recorded very slowly so that you can understand better, and that's it.